All right. Welcome, everybody. This is it. Learning Rust. We're going to do Chapter 5 today. Thank you for popping in the stream. I'm Tom McGurl, here again to teach you some more Rust. Well, not teach you, learn with you, right? Not teaching this time. We're learning together. You can see below, we got the Twitter handle. Follow me on Twitter. You'll get alerts every time I go live for streaming ahead of time and right when we go live. Check out the GitHub. That's where you're going to find the repo for our Learn Rust Live, as well as the other repositories that we've done on the stream. I'm going to go ahead and share my screen here. We got the YouTube channel over here. Check this out if you want to see any of the videos you may have missed from the past. So you can see here we have the past Rust sessions. We got the live coding, building a serverless API with AWS Lambda, DynamoDB, S3, using Node and TypeScript to build that. We have the chapters 1 through 4, as well as the practice problems that we went through together. You could find those here as well. And then before that, we did a little React Native, learning Recoil.js with TypeScript, Expo, and of course, React, Recoil.js, and React Native. So that was really fun. That was a big series, so a lot to go through, but very fun. And now we're here. You're here trying to become Rustaceans. We're learning together. It's been pretty fun. A little challenging at times, but definitely fun. And just been really enjoying it. Luckily, we have this amazing book to go off of. Again, I mentioned the Twitter. You could find that here. We'll be posting live updates here. We got this cool, my man Clam Watson. This is Buddy built this. It's an awesome emulator. Check it out. And then we got the repo here for Learn Rust Live. This is where you can find the code base, pull it down, try the stuff yourself. And of course, what we're going to be doing again is going through the Rust programming language book. It's an amazing book. Really wanted to give a shout out again to the authors. We have Nichols Matsakis and Aaron Turan. Awesome job. I mean, we've been loving this book. Couldn't do this without you, and I'm sure the rest of the Rust community that contributed to this. So just a quick shout out for anyone involved in this book. It's been fantastic. It's been really helping me learn. I hope it's been helping all of you learn. And again, couldn't be here doing this without it. So let's jump in. You may notice a difference in the stream tonight. I'm pretty excited. I'm streaming from my Windows, my gaming PC at the recommendation of Clam Watson in the chat. We're going to see hopefully some better quality. I got a little higher output going. You should see a little better video quality on the output stream, as well as the uploads going into YouTube. So that'll be great. We're going from trying to get that 1080p. So that'll be pretty awesome. And because we're on Windows today, you're going to maybe see me struggle a little bit, but mostly we're going to be using Windows Subsystem Linux 2, the new version. We're running a Ubuntu VM where we have hooked VS Code into. And so I'll be able to use all the same commands I'm familiar with my normal terminal and things like that. So should be pretty cool. I've got VS Code hooked up, and let's see how it goes. All right, so let's do a quick little recap because we've done a lot. I don't want to recap everything, but just kind of catch up to where we're at, where we left off a bit, just to kind of see how things are. So we've done chapters 1 through 4. Chapter 1, intro, right? We jumped in, learned a little bit about just what it's like installing it, setting it up, installing Rust up, right? Getting cargo going. Chapter 2, really fascinating chapter. They had us dive right in. We just started writing code. We made a guessing game that you can find here in our projects folder here. We have our guessing game. Let me just move this over so we can see it a little better. I don't need that full length. So we have our guessing game. This was fun, right? We got to build a guessing game like right off the bat. That was really cool. And then we jumped into chapter 2, where they kind of related Rust concepts to concepts that we may already be familiar with in other programming languages. Again, if you're not coming from another programming language, they'd all be new to you, but it really helped, my background in JavaScript, as well as some, Python and other languages. It was useful to see how those, relate to each other. We then hit up chapter 4, where we actually dove into a concept that is unique to Rust, the ownership concept. And it's how that Rust handles passing values and handles memory, right? So it's how it allows us to transfer ownership of a variable, or let's say ownership of, some sort of object, whether we've created a string, right? Something we've allocated on the stack, or something we've allocated on the heap, something more complex like a list, and how we can pass ownership to functions. We also learned about the copy trait and what that means, and we compared that to kind of JavaScript's pass by value versus pass by reference. So really cool stuff. Again, that's what's going to handle memory management. Remember, we don't have garbage collection in Rust, so we need other ways to handle and make sure we're doing things in a safe way. After that, we learned about slices. So we learned about how to create lists or strings and how to grab slices of those strings. And you can find that in our slice type project here, where we're actually looping over bytes in an array and bytes in a string and breaking it up into different word chunks. Then we went back to chapter 3 and did some exercises, and you can find those here as well. We did a temperature converter, which was a lot of fun. You basically type a temperature and it'll tell you, if you type it in Fahrenheit, it'll give you the Celsius and vice versa. And actually, if you want to see what that looks like, I can pop myself up over here, go in here and run cargo new. And here you can see, not cargo new, I want cargo run. Here you can see, please input a temperature. So I can put 32 Fahrenheit and it'll say 0 Celsius. I could do the same backwards. So I could say, give me 100 Celsius. And I just picked ones I'm familiar with. So 212 Fahrenheit. So pretty cool stuff. And this is really fun. And now we're going to be diving in to learn about structs. We did run into a situation where structs would have been useful, but we ended up using a tuple, which is kind of like a form of a struct, to handle our Fahrenheit Celsius conversion. If you remember, we had our get temperature from string function return a tuple of a 64-bit integer signed and a string. And again, this is a string slice, which we learned about in chapter 4.3 to be precise. So let's dive in without further ado, right? We're going to go into chapter 5 and let's learn about structs. I'm excited. I hope you're excited. Let's go. All right. A struct or a structure, custom data type that lets you name and package together multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples, which we used, with structs, demonstrate how to use structs, and discuss how to define methods and associated functions to specify behavior associated with structs data. So it's already starting to sound like a class, maybe a little bit, or an object, so in other languages. Structs and enums, discussed in chapter 6, are the building blocks for creating new types in your program's domain to take full advantage of Rust's compile time type checking. Again, that's some of the beauty, right? We're getting those amazing compile messages, compiler errors when we have compile issues, and this is what the type safety we're going to get from Rust. So I'm excited. All right, defining and instantiating structs. Woo. Let's see. Structs are similar to tuples, right? We've defined those here. Here we're returning a tuple, which we're discussing in chapter 3. Like tuples, the pieces of a struct can be different types. So we see that here where we have a signed 64-bit integer and a string slice in our tuple. Unlike tuples, you'll name each piece of data so it's clear what the values mean. As a result of these names, structs are more flexible than tuples or tuples. You don't have to rely on the order of the data to specify or access the values of an instance. Okay. And they have the definition of a struct down here. So we use the keyword struct. A struct's name should describe the significance of the pieces of data being grouped together. So this is kind of like a class, I'd imagine, something like a class. Then inside the curly brackets, we define the properties, the names and types of the pieces of data, which we call fields. So they call them fields. And in 5.1, we have a struct that stores information about a user account. Cool. I'm going to go ahead and create a little cargo project so we can try following along a bit within our code. And this way it's in the repo if anyone wants to try it out. So let's go ahead and open this. I'll just pop myself over here so I'm out of your way. And we're going to go back up a level here. We're in our projects directory and we're going to do cargo new. And I apologize for my terminal formatting yet. I didn't have time to adjust my Ubuntu terminal to look like my nice fancy one that I had before. Next time, all right? Relax. Relax. All right, so we're going to go ahead and call this structs. So we have our new structs project here, and I'm going to go ahead and open main, and we'll just start typing away. So I'm going to go ahead and add this struct user, and we have username, and we're defining the types right here. So we're saying username is a string, email is a string, and this looks similar to a TypeScript type. If you were with us when we did our TypeScript programming, either in building our AWS Lambda function, got to set up the .files repo. I do have a .files repo. but not all, and I have instructions on how to set up my terminal, but not all of the ZSH and the bash scripts do not cover all of my settings. There's some stuff, unfortunately, that is not in there, but I do. And you can check it out. It's open source. It's called Setup. Sign in, but that is a pro move. If anyone is wondering what we were talking about there, a .files repo is a repo where you can put all of your configuration files that you can share so that people can, well, not people, but you can have them from machine to machine. And so I have one, I call it Setup, where I have not only my .files, but my editor configurations that I've exported from Sublime Text in the past, Atom, now VS Code, as well as some basic things for when I set up a new PC, the things that I install, and some of the documentation that I followed. So you can check that out. Unsigned 64-bit integer. So this is different than the F64. Remember, the F64 is signed, so our count can never be negative. Active is a Boolean, so true or false. All right. So a user struct definition. So to use a struct, after we defined it, we create an instance of that struct by specifying concrete values for each of the fields. So it's kind of like we're doing like an instantiation of an object, if you're familiar with JavaScript. And if you're familiar with Python, like having a class, right? We create an instance by stating the name of the struct and then add curly brackets containing key value pairs, where the keys are the names of the fields and the values are the data we want to store in those fields. So they're going to have to match the types. So username will have to be a string and so forth. We don't have to specify the fields in the same order, though, in which we declare them in the struct. That's pretty nice. In other words, we can even though we declare them as username, email, we can provide them in any order. In other words, the struct definition is like a general template for the type, and instances fill in the template with particular data to create values of the type. For example, we can declare a particular user as shown in listing 5.2. So let's check out listing 5.2. So interesting. We have the string from, that's going to create the capital S string type, right? Username, email, they're doing it out of order, active, true. So let's try that out. Let's do that down here. So let's create a user. So this is interesting. So we're not, in something like JavaScript, if we were creating an instance of a class or something, we'd do user. But again, this is just a struct. It's just describing the type of this thing, right? So it's different. It's closer to a TypeScript type. So what we say is we're going to do user, and we're going to go ahead and define something in line. So I'm going to say email is string from younggods117@twitch.tv. I just made that up. And then these are comma separated, username, string from. We're going to do we're going to do the use as v's because I think it's funny. Young God. Cool. And then we're going to do active Boolean. We're going to say it's true. And sign in counts. We'll do 1 as well. Again, that's it. A signed 64-bit integer. If I did this, let's see, would it complain? Let's try. So first, let's go into our structs and we'll do cargo check. Yep, cannot apply unary operator because it is unsigned. If I run cargo check again, and again, cargo check is just going to check that it compiles. And all it's saying here is, hey, you have to put a semicolon. Cargo check, and we're good. It compiled. So cargo check is just an easy way to check if it compiles without running the program. All right, awesome. To get specific value from a struct, we can use dot notation. Familiar with that, right? If we wanted just the user's email address, we can use user1.email. Whenever we want to use this value, if the instance is mutable, we can change a value by using the dot notation and assigning into a particular field. Okay, so this is pretty cool. Different than something like I've dealt with other languages where we had immutable objects where you couldn't just modify it using dot notation. You had to use almost like a spread operator. I'm thinking of something like Elm or Haskell. Listing 5.3 shows how to change the value in the email field of a mutable user instance. So this user is not mutable, so we can make it mutable and then we'll change the value. So let's try that. So first what I'm going to do is I'm going to make it mutable, and then I just want to print the email. So we'll do print. Oh, and you know what I just realized? I don't know if I have my, since I'm on Windows, let me just check. I don't know if I have my Rust thing installed. I did sync my settings, but appears, oh no, it's there. I don't know why it didn't autocomplete. Interesting. So let's do print ln. and we're going to provide it. We'll say users email is, and then again, we're going to say user1, and we're going to access it with dot notation, email. And so let's run that, cargo run. And there it is, user's email is young god. And so here it's saying the field is never read, and that's just saying we haven't used them. So we stored them, but we never used them. No big deal. Okay, now let's try changing the value as they've done here. So we're going to say user1.email, or let's change the username. Let's say username is, and we'll do string from, and I'll just use my name. And then I'm going to go ahead and print the username here. Oop. Just get rid of some of this extra space. And we'll say user's name is username. And we will clear this out. Get this out of your way here. And let me just scroll that so you can see that. And let's run cargo run. Oh, unexpected token. And that's because I need a semicolon here. And I'm getting used to that. So let's say cargo run. And username is Tom McGraw. Great. All right, so pretty cool. Note that the entire instance must be mutable. So we didn't just say that a piece of it is mutable. We made the whole instance mutable. Rust doesn't allow us to mark only certain fields as mutable. As with any expression, we can construct a new instance of the struct as the last expression in a function body to implicitly return that new instance. We'll just leave the semicolon off. List 5.4 shows a build user function that returns a user instance with the given email and username. The active field gets the value of true by default, and the signing count by default gets the value of 1. All right, let's try that. So let's create a new function called build user, and it'll take an email of type string, username of type string, and it will yield or return type user. And we're gonna just do what they have here, where we say, I'm just gonna go ahead and copy this. Oop. Paste that down here. And what I'll do is I will say email is going to be equal to email. And what I'm interested in is if I can do similar to something we do in JavaScript, where if I can just, since these are the same, maybe I can just do this. And I think I just spoiler alerted us because I'm seeing it down here. Predictions, the predictions, right? Wow. That's awesome. So let's see what we did there. It makes sense to name the function parameter the same name as the struct fields by having to repeat email and the username field is a bit tedious. So what it allows us to do is use this shorthand. So because the parameter names of this field and the variable that we're setting it to, right, are exactly the same, we can use the field init shorthand syntax to write that. So that's why we're able to say email here instead of email like that. Now, if this was something different, this would no longer work. I'd have to specify here. But since we were saying we're just using email, we can simplify it. So it's pretty cool. It's a nice little shorthand. If you've worked with JavaScript, you've seen it. If you've worked with Python, you know it's not there. A little Python shade, whatever. Maybe there's some version I'm not using and it is there and I don't know about it. Easy, just make the change. Come on, Python, let's go. All right, so pretty cool stuff. So we have our build user. Let's just go ahead and call it and test it out. So I'm gonna say let's mute user2. We don't need to make it mutable. Let's just use it as is. Equal build user, and we're gonna pass it an email of test.testington.com. We'll say test@testington, right? We gotta make it an email, and we'll make the username testingsworth. All right, and here what we'll do is we'll print ln, and we'll say user2's. We'll say user2 email, and then we'll put the email first, like that. Sorry, fingering, and then user, and then we'll say username, and we'll just do that. And then again, we'll say user2 dot email, user2 dot username. And let's try it out. I gotta put a semicolon here. Let's put a semicolon here. And let's cargo run it. All right, so it's complaining, and that's because I created a string literal. Remember, we're using the string type, so we're gonna do from, like that. All right, that should do it. Clear that out, cargo run. All right, so now it's saying not found in this scope, cannot find struct, variant, or union type user in this scope. So that is likely because user, we have here user, let's see. Let me read that again just to make sure I get what it's saying. Cannot find type user in this scope, not found in this scope. So I'm assuming it's likely because this exists outside our main. So let's try putting it in our main where we've actually defined that struct, and we should be able to use it then. Oh, let me just go ahead and do this. Why is my tab not working? Interesting. This is painful. Something's wrong with my keyboard shortcuts as when I translate it over here. All right, let's just clean this up here. And then we would need to do an extra one there, 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 there. Woo! Sorry about this mess. Oh, you know what it probably is? No, I don't know what it is. Let's let it format it for us. So let's do cargo run. And there we go. User's email testington.com. Username testingsworth. So pretty cool there. All right. So we have our build user function. Here we're creating a new instance of the user struct, which has a field named email. We want to set the email field's value to the value in the email parameter of the build user function. Because email field and email parameter are the same name, we only need to write it once. So that's what we just covered. Okay. So creating instances from other instances with struct update syntax. This could be cool. This could be cool. What's this about? It's often useful to create a new instance of a struct that uses most of an old instance's values, but changes some. You'll do this using struct update syntax. So this is kind of what I was thinking of when I was talking about spreading or just updating a single value, but pulling the rest of the other values. So it shows how we create a new user instance in user 2 without the update syntax. We set new values for email and username, but otherwise use the same values from user 1 that we created in 5.2. So here you have user 2, email, username, and then we're assigning active to user 1's active and sign in to user 1's sign in. Now we can use what looks like a spread in JavaScript, but instead there's only 2 dots. And it's saying use these values and then use the rest of the values, get them from user 1. That's pretty cool. I like that. That's pretty awesome. That's very, very cool. So it's like you can spread another object's properties in and it'll replace only those properties. If you specify properties, it will not replace them. So that's pretty cool. Using struct update syntax to set email and username values of the user. It also creates an instance in user 2 that has a different value for email and username, but has the same values for active and sign-in count that user 1 has. Very cool. So let's try that really quick. So we have our user 1 and our user 2. So let's go ahead and create, I'm going to call it inactive user 2. And what I'm going to do is I'm going to say it's a user that's going to have active set to false, but then everything else I want to get from user 2. And what I'm going to do here is I'm going to print user, let's put inactive, let's do it like this. Inactive user 2 info, and I'm just going to say active. Let's do this, active, and I'll put active there, and then I'll put username, just so we can see that the values are in fact copied. And so what I'll do is I'll do user inactive user 2 dot active inactive user 2 dot username. And again, we're going to put a semicolon there, clear this out, run cargo run, And there we go. Inactive user to active false because we made it inactive, and the name carried over. So pretty cool stuff. Definitely convenient. I like it. It's something familiar. It feels good. It feels easy. I like that. I hope you like that, right? Pretty great stuff. Using tuple structs without name fields to create different types. All right, let's see. You can also define structs that look similar to tuples or tuples, called tuple structs. Tuple structs have the added meaning tuple structs have the added meaning the struct name provides. So they get the name that the struct provides, like user, but don't have names associated with their fields. So it's almost like a named tuple, just like a named tuple. Rather, they just have the types of the fields. That's pretty cool. Tuple structs are useful when you want to give the whole tuple a name and make the tuple be a different type from other tuples. And naming each field as in a regular struct would be verbose or redundant. So you can see here, they use the perfect examples. Color, point, right? You have like an RGBA color. Point, X, Y, Z, right? So this is a really cool use case. I like this. To define a tuple struct, start with the struct keyword, and the struct name followed by the types in the tuple format. So with the parentheses. For example, here are the definitions and usage of two tuples structs named color and point. This is pretty cool. And it makes sense. I'm going to create a new function here for this. And we'll call this function tuple structs. Just so I have it, just like as a separate space. And we'll go ahead and create struct color. We're doing RGB, so we got in this case, a signed 32-bit integer, which is interesting. I guess you can get negative values there. And there we go. So color, that's cool. And then point, just like a coordinate, right? That's what we're thinking here. Oop. Oh, what's going on here? Here we go. My Vim bindings are all wacky. Point. So there we have a color and a point. Very cool. And let's instantiate. Let's create a color. So let's say we are here saying let black equal color 0, 0, 0, and then let origin equal point 0, 0, 0. So pretty cool. These are tuple structs. So you can imagine color and point. This is a good one. You could have a coordinate that's just X and Y. That's like probably a good use case for this. We could create our own thing. Like we could say, I've done some functional programming where I built a Tetris, right? And you describe all your tetranumos as their coordinates, right? The coordinates of where their blocks are. So you have the tetranamo that's like just the square, right? So you have 0, 0, 0, 1, 1, 1, right? The coordinates. And then you have the one that's like the one on top of the 3 below. And so you could describe a tetranamo as a series of the locations of the blocks. So something like that. A blood type, right? Anything. So basically things where it's pretty obvious by the name what's going to be in them. So it's pretty cool. I like it. Note that black and origin values are different types because their instances are different, tuple structs. Each struct you define has its own type, even though the fields within the struct have the same type. So just because they both are tuples of, in this case, signed 32-bit integers, it doesn't mean they're the same because we've named them differently. They're a different namespace. So yes, in theory, they contain the same types, but they're not the same. So, and this is what they're saying here. For example, a function that takes a parameter type color cannot take a point, even though they both contain the same types of data as an argument. Otherwise, tuple struct instances behave like tuples. You can destructure them into their individual pieces. You can use a dot followed by the index to access individual values and so on. So we could say let x, y, z equal origin, right? And that would give us the individual values, just like we could say let r, g, b equal black. And this kind of shows you what the values are without us naming them, right? Like XYZ, RGB. So kind of cool. And then the dot notation would be .0, .1, .2, right? unit-like structs without any fields. Interesting. You can also define structs that don't have any fields. These are called unit-like structs because they behave similarly to the unit type. That's that empty parentheses thing we've seen a few times. Unit-like structs can be useful in situations in which you need to implement a trait on some type but don't have any data that you want to store in the type itself. We'll discuss traits in chapter 10. I knew it. We know about one trait. We know about the copy trait. We learned about that. Okay, ownership of a struct. Here we go. Look at this. Rustation is coming out. He's got the question mark. It doesn't compile. We know what that means. Let's go. Ownership of a struct. Data. In the user struct definition list in 5.1, we used the own string type rather than the string slice, right? This is a deliberate choice because we want instances of this struct to own all of its data and for that data to be valid for as long as the entire struct is valid, all right? It's possible for the structs to store references to data owned by something else, but to do so requires the use of lifetimes, a Rust feature we'll discuss in chapter 10. We're halfway there. Living on prayer. Lifetimes ensure that data referenced by a struct is valid for as long as the struct is. So again, let's read that. That's important, I think. Lifetimes ensure that the data referenced by a struct is valid as long as the struct is. So any data that struct references is valid as long as that struct is. Let's say that you store a reference in a struct without specifying lifetimes like this, which won't work. Let's look at what they're doing here. And in fact, what we'll do is let's follow suit here. So let's declare, well, first of all, I'm going to move user outside of main here so that we can use it in multiple places here. Whoa, didn't want that. And then we can move this back out, right? All right, and that'll work now because it's outside the scope. And so what we're going to do here is we're going to change user. Well, actually, you know what? Let's do it in a different file because I want these to still work. And they might actually because, you know, they would because string slice is still, remember, string slice and string, it's still valid. So let's try this. So let's go ahead and we'll close that out. So let's change our string type here to a string slice. And same thing here. And these remain the same. And user one, we're going to change from, we're just going to get rid of this whole stuff here, right? You can jump over here, get rid of that. And same thing here. All right, so now we have a regular string. Okay, so now it's going to say the compiler will complain that it needs lifetime specifiers. Let's see that it actually does that. So let me move over here in the top left to get out of your way there. And we'll do cargo check to see that error. All right, so here we see it. Let's start from the beginning. Missing lifetime specifier. Yo, they act like we didn't know. Come on, we're Rustations here. We know it was missing lifetime parameter. We're 5 chapters in. We're calling us Rust people. Come on. Expected a lifetime parameter. Consider introducing a named lifetime parameter. Check this out. Let's see what the message tells us. Then we'll look at the book. Let's see if we can get anything from the message because these messages tend to be pretty good. Consider introducing a named lifetime parameter. And they have an example here. Struct user A. Username reference A str. And then the same thing here. Missing lifetime specifier. Email string. Expected name lifetime parameter. Consider introducing a named lifetime parameter. And here it is again with the A. Aborting due to 2 previous errors. For more information, try Rust-C explain. Ooh, that's pretty cool. So we can try explain the error. That's pretty, let's try it. Why not, right? It gives us that nice error. Let's try it out. Wow. This is pretty neat, people. Come on, this is pretty neat. This error indicates that a lifetime is missing from a type. If it is an error inside a function signature, the problem may be with failing to adhere to the lifetime elision. I don't even know that word. Yo. Not gonna lie, I don't even know that word. Elision rules. Don't even know it. Erroneous code examples. Expected lifetime parameter. This is a correct version. Expected lifetime parameter. This is a correct version. So this, let's look. Pretty cool that we can do all that stuff. Let's see what the book says. The compiler will complain. In chapter 10, we'll discuss how to fix these errors. Come on. We should discuss it now. Well, we know how to fix it. We could just, we could fake it, right? We could say, what did they say to do? We'll just copy what they said to do. So let's try that. Let's just steal what they said to do. So say user, and this is not how you should program. Don't do this. Find out what it actually means, please. But for now, for fun, we're going to go ahead and try it. Why is it only telling me to do it on email? Well, let's see. Let's see. Ooh. Oh, because we're using it again. Let's wait. This is not good practice, right? We should learn what it does so we understand and we don't cause. Again, we're trying to create safe programs. All right, an example program using structs. Ooh. Let's check this out. To understand we might want to use structs, let's write a program that calculates the area of a rectangle. Classic. We'll start with single variables. Let me move myself here so I'm out of your way. I'm always in your way. Come on. We'll start with single variables and then refactor the program until we're using structs instead. Very cool. I'm excited. Hope you're excited. Let's make a new binary project with cargo called rectangles. Let's do it. So we'll go down here in our terminal. Let me move myself. Clear this out. Cargo, let's back up a little bit. Cargo new. What are we calling it? Rectangles. Get into rectangles here. All right. Let's check it out. Rectangles. Main, there you go. There's our hello world for rectangles. Pretty neat, pretty easy. Let's go. All right. We made a new binary called rectangles that will take the width and height of a rectangle specified in pixels and calculate the area of the rectangle. Easy enough. It shows a short program with one way of doing that, exactly that in our project's main. So this is going to use integers. So we're not using a struct yet. So let's code up this way, and then we'll refactor it, which type systems help with. That's another big thing, right? Type systems actually really help us with refactoring. Because they complain when stuff breaks. So if we get it working, it helps with refactoring. Just like tests, right? Unit tests. You have unit tests, they help you refactor because they tell you when something breaks. Type system is going to help us with that too. So let's see. All right, so let's go ahead and code this up here. So we have let width 1 equal 30. Let width, or height 1 equal 50. And these are in pixels. And then we're going to print ln, what are we printing here? The area of the rectangle. The area of the rectangle is square pixels. Robot voice, and then we're going to call a function that doesn't yet exist. We're going to write it in a second. And we're going to go ahead and return that. And then we have a function down here called area. It's going to take a width that is going to be an unsigned 32-bit integer. Again, we're not going to have negatives, right? So we use unsigned. It's always good to specify based on your use case. And we're going to return a single unsigned, right? We can have a negative area. Black holes maybe, but not here. And we're just going to do classic width times height. And we're going to leave off semicolon. We're going to leave off return. We're going to leverage and lean on that implicit return here. All right, let's run it. Go down here, cargo run. Let me move out of your way. Cargo run. The area of the rectangle is 1,500 square pixels. Just 5, right? 50 times 30. Perfect. All right, very cool. Now let's refactor. Let's use structs. That's why we're here. Come on. We ran cargo run. We saw it worked. It does work, and it figures out the area. We can do better. It says we can do better. It's like, you can do better than this. You know, when your parents say, you know, it's pretty good, but you could have done better. You could do better. The width and height are related to each other because together they describe one rectangle. Makes sense. The issue with this code is evident in the signature of area. Area signature takes a generic width and height and returns a single unsigned 32-bit integer. It's supposed to calculate the area of one rectangle, but the function we wrote has two parameters. Parameters are related, but that's not expressed anywhere in our program, right? you could just pass anything. Actually, in this case, it's almost like it's just unsigned integer multiplication. It would be more readable and more manageable to group width and height together into a rectangle struct. We've already discussed one way to do that in the tuple type, right? We could use tuples. We could use a name tuple. We could use a bland tuple without a name, or we could use a struct. So let's refactor it with regular tuples. So unnamed tuples, we're not talking about struct tuples, just the unnamed regular ones. So let's refactor. So we're going to go ahead and say let rect1 equal 30, 50, and we can get rid of this, and we can refactor this where this will take a tuple. We'll call it it's going to say we want to call it dimensions, and it's going to take a tuple of type 32, unsigned 32-bit integer, and it's going to return a single unsigned 32-bit integer. And here what we're going to do is we're going to access the values here. And so the way they're doing it here is dimensions.0 times dimensions.1. We could also do let width height equal dimensions, and then we can return width times height. I like that a little bit better. It's one extra line of code, but it's a little more readable. Although in this case, they could have passed the dimensions in any order. Doesn't matter though, it's just multiplication. Let's try this. Let's try our way and see. Cargo run. We got an error. Let's read it. Oh, cannot find the value. That's because we did this. So we want to say area rect1. So these error messages, fantastic. Loving them. All right. Let's go ahead and clear this out. Let me run over here. Cargo run. There you see it. The area of the rectangle is 1,500 square pixels. So that worked. And again, this is the other way to do it, which will also work. So just two different ways of accessing the two values inside the tuple. All right, back here. So that's one way. In one way, this program is better. Tuple lets us add a bit of structure, and we're now passing just one argument, just that rectangle. But another way, the version is less clear. Tuples don't name their elements, so we don't know what the order is. Could be width height, could be height width. Luckily, it doesn't matter because we're just multiplying it regardless. But imagine if the formula was different, right? So here, it doesn't matter if we mix up height and width, right? But if we want to draw the rectangle on the screen, it would matter. We would have to keep in mind that width is the tuple index 0 and height is the tuple at index 1. If someone else worked in this code, they would have to figure this out by reading the code, right? It would be easy to forget and mix up these values and cause errors, but because we haven't conveyed the meaning of our data in our code, and there's nothing here restricting us from making that mistake, right? There's nothing protecting us from making that. The compiler's not going to catch that if you flip them. Refactoring with structs, adding more meaning. We use structs to add more meaning behind. We add structs to add meaning behind labeling the data. We can transform the tuple we're using into a data type with a name for the whole as well as names for the parts, as shown in listing 510. So let's do that. We're going to create a struct called rectangle, the moment you've all been waiting for, obviously. And we're going to go ahead and put a width. And one thing I've noticed right off the bat, I have to change my settings on here because my spaces are only 2. But remember, we want 4. And I did this on the Mac side, but I just want to also do it now on the Windows side. And I'm surprised that setting didn't carry over because we're using setting sync, but it's for another day. So unsigned 32, height is going to be unsigned 32. Separate that by a comma. And here we're going to let rect equal a rectangle. And instead of this, we're going to do that. And we're going to say width is 30 and height is 50. Pretty cool. That's pretty cool. Arby's is pretty cool. Maybe too young for that video. All right, rect1. Let's run it. Get out of your way. Cargo run. Let's see what we get. So we have an error. expected tuple found struct. So that's because we have to change the function arguments here. It now takes a rectangle. So we can change this here. We can say, let's do this. Rectangle, and it's going to take type. And so here we're saying it's going to take a reference to a rectangle. Remember, we're dealing with ownership, right? We're dealing with structs. So we don't want it to take ownership. So we're going to pass a reference to a rectangle. It's going to return an unsigned 32-bit integer. We don't want it to take ownership of the rectangle. We just want the new thing back. And so here we'll also pass a reference to the rectangle. What's the difference here? Well, if we didn't do this, we wouldn't be able to use rectangle afterward. I wouldn't be able to print it. Like down here, I wouldn't be able to take pieces of it because the ownership would have gone to the area function. In this case, we just pass a reference, so when area is done, it relinquishes ownership back to our main function. Again, this is chapter 3. Sorry, chapter 4.1 and 0.2 go over this in detail. But so here I'm going to pass the rectangle, and here instead of dimensions, I'm going to say rectangle. Cool. All right, let's test it out. Cargo run, error, rectangle 0, rectangle 1. That's because we are no longer using that. We actually can use the names now because we are using a struct. So we're going to say width, and we're going to say height. Let's go clear that, and let's do cargo run. And there we go. The area of the rectangle is 1500 square pixels. Now let's look at what we did here. So we made it more readable, right? We have a structure called a rectangle. You can think of it as like a type, right? And we are creating a rectangle here, passing it to our function. Much more readable, right? It's going to be much more difficult to mess up width and height here. You'd really have to not know the difference to get them messed up. So pretty cool. Here we've decided, and the book's saying, here we defined a struct and named it rectangle. Inside the curly brackets, we define the fields as width and height, both of which have a type unsigned 32-bit integer. Then in the main, we create a particular instance of rectangle that is a width of 30 and a height of 50. Our area function is now defined with one parameter, which we've named rectangle. So pretty cool. The area function lets us access the width and height fields of the rectangle. This part's important here. As mentioned in chapter 4, when we mentioned this, we want to borrow the rectangle and not take ownership of it. This way, main retains its ownership and can continue using rect beyond that actual function call to area, which is the reason why we use the ampersand to pass the reference. All right, pretty cool. Adding useful functionality with derived traits. Derived traits. Here we go. We're going to get into derived traits. Should be fun. All right, so let's see. It'd be nice to be able to print an instance of rectangle while we're debugging our program and see the values for all its fields. Right now, you'll notice we're printing area. If I wanted to print rectangle before, like we were doing here, we were printing individual parameters one at a time. It would be nice to print them all. Similar to something we would do in JavaScript, right? You could stringify a JSON object. You can console log a JSON object. I'm sorry, you can console log an object. Sometimes you'll see, object is the syntax. You can console.dir an object where you actually print it out, or console.table, which is even better. So something probably like that is what we're looking for here. To see all the fields. So it says here, while we're debugging our program to see the values of all fields, this listing here tries using println, the macro, as we used in the previous chapter, but it says it won't work. So let's go ahead and see what's going on here and why it won't work. So we have a rectangle. I'm going to create another rectangle down here. I'm just going to actually change. I'm going to add a line here. Like, I think that's all it really did. Add a line here to print rectangle 1. Rect1 is, and if we run cargo run, rectangle cannot be formatted with the default formatter. So this is kind of like something you'd see, in Python or JavaScript if you try to print something that's not serializable. So in JavaScript, we'd be talking about an object or some kind of structure that doesn't have a toString function. And in Python, you'd be talking about also an object or structure that cannot be serialized, right? It cannot be converted to a string and therefore printed. So That's something like what we're getting here. So let's see how we can get past that. All right. The print, so it says it actually right here. Did we see that? I didn't know if I saw that part of the message. Let's see, cargo run. Cargo run. Oh yeah, so it does say that on my end. It says display is not implemented for rectangle. So this is kind of like that toString is not implemented almost. It's a trait. So pretty cool. All right, let's look into what that's all about. The print macro can do many kinds of formatting, and by default, the curly braces tell println to use formatting known as display. Output intended for direct and user consumption. The primitive types we've seen so far implement display by default, such as string, integer, because there's only one way you'd want to show one or any other primitive type to a user, right? And strings, there's only one way that we would display them. It's like as is. But with structs, the way println should format the output is less clear because there are more display possibilities. Like we just mentioned, console.dir, we can display it as a table, right? You can display it as a CSV, many different things. Do you want commas or not? Do you want to print the curly brackets? Should all the fields be shown? Due to this ambiguity, Rust doesn't try to guess what we want. And structs don't have a provided implementation of display. If we continue reading the errors, we'll find this helpful note. Help. The trait standard format display is not implemented for rectangle. Note, in format strings, you may be able to use curly sign, blah, blah, or that for pretty print instead. So interesting. So we can use this or this for pretty print. Let's try it. The println macro call now will look like this. So instead of this, we can say this. Let's try that. So we're looking right here. We're going to try this first one, and then we'll try the second one. So let's see what this prints out. Let me make this a little bigger. Cargo run. Oh, sorry, I changed the wrong spot. So it colon that. All right, ready? The moment of truth. Rectangle cannot be formatted using blah, blah, blah. Okay, so let's see. What does it say here in this book? Putting the specifier inside the curly bracket tells println we want to use the output format called debug. The debug trait enables us to print our struct in a way that is useful for developers so we can see its value while we're debugging our code. Compile the code with this change. Drat, we're still getting error. Rectangle doesn't implement standard format debug. Interesting. But again, the compiler gives us a helpful note. So let's see what the helpful note is. So we can see here, add derive debug or manually implement standard format debug. Note, required by standard debug format. This error originates in a macro in nightly builds run with, okay. So we can implement standard format debug and specify how that should be displayed, or we can add derive debug. Rust does include functionality to print out debugging information, but we have to explicitly opt in to make that functionality available for our struct. To do that, we add the annotation #derive debug just before the struct definition. All right, seems a little complicated, but let's see. So we would add that. It's almost like, so it's an annotation. If you are familiar with Python, you will have probably come across annotations, or other languages that have these. I can't think of any off the top of my head, but it's a pretty common thing. Debug. So here we're annotating, which I'm assuming says, hey, this thing should have the standard debug. And let's try it. Ready? Let's clear this out. Cargo run. Did I do it right? Derive, debug, capital D. All right, clear that out. Let's try it out. Cargo run. And there we go. We get rectangle is rect with height. And let's see if I add that pretty print, which they mentioned before. Cargo run. Much better. That's more of like what I would expect. So pretty cool. And you can see that here. When we use the style example, the output will look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114 Very cool. Rust has provided a number of traits for us to use with the derive annotation that we can add useful behavior to our custom types. Those traits and their behaviors are listed in Appendix C, so we can check that out. We'll cover how to implement these traits with custom behavior as well as how to create your own traits in Chapter 10. Our area function is very specific. It only computes the area of rectangles. It would be helpful to tie this behavior more closely to our rectangle. So right now it's a separate function, but maybe we can just tie it to the rectangle because it doesn't work with any other type. Let's look at how we can continue to refactor the code by turning the area function into an area method defined on our rectangle type. Here we go. All right, so let's jump in there. Let's see, next part. We're coming along here. Method syntax. So we've touched upon this before, right? We've used it. We just haven't dove into actually what it is or how to write it. So this will be cool. Methods are similar to functions. They're declared with the fn keyword and their name. They can have parameters and return a value, and they contain some code that is run when they're called from somewhere else. However, methods are different from functions in that they're defined within the context of a struct or an enum or a trait object, which we'll cover in chapters 6 and 17, respectively. And their first parameter is always self. So this, right away, come on. Very similar to other languages there, which represents the instance of the struct the method is belonging to, or the method is being called on. All right, let's see. Defining methods. Let's change the area function that has a rectangle instance as a parameter and instead make it an area method on the rectangle struct. So we got our derived rectangle here. So we're going to go ahead and say impl rectangle. Interesting. Function area. Oh. And it takes a parameter. Its parameter is self. It could probably take other parameters. But in this case, it has all the information it needs right in the struct. So this is good enough. And it's going to return self.width times self.height. And again, leaving off the semicolon, leaving off the return, we're going to use that implicit return. All right. And then here, instead of calling rectangle, we can get rid of this here. I'm just going to comment this out because I think this is valuable for us to have here for later. I'm also just going to comment this out, and I'll just copy it so that we can reuse this code basically. And uncomment that. And instead of calling rect1, we're going to call rect1.area. And let's clear that out. And let's run cargo run. Jump the gun a little bit. Not found in this scope. Rectangle, rect1.area, impl rectangle. Let's make sure we did this right. Function area, self returns 32-bit signed integer. All right, let's see what's going on here. Rect1. Cannot find function area in this scope. All right, let's keep reading. So to define the function with the context of rectangle, we start with IMPL implementation block. Then we move the area function within the implementation curly brackets and change the first, and in this case, only parameter to be self in the signature and everywhere within the body. So we got rid of the rect and used self. In main, where we called area function passed it the rectangle one's reference as an argument, we can instead use method syntax to call area method on the rectangle instance. The method syntax goes after an instance. We add a dot followed by the method name in parentheses to invoke the function. So let's see why. Oh, it's because I tried passing it to area. Duh. So let's get rid of that here. And let's clear this out and run cargo run. Bam. Very cool. In the signature for area, we use self instead of rectangle because Rust knows the type of self is rectangle due to the methods being inside the implementation rectangle context. So pretty, makes sense. Note that we still need to use the ampersand before self, just as we did in rectangle. Methods can take ownership of self, borrow self mutability as we've done here, and borrow self mutability just as they can any other parameter. That's pretty interesting. Definitely Subtle thing, but makes sense. So methods can take ownership of self. We've chosen at ampersand self here for the same reason we used rectangle in function version. We don't want to take ownership. We just want to read the data of the struct, calculate the area, and return that, not write to it. And we wanted to change the instance that we've called the method on as part of what the method does. We'd use the mutable reference as the first parameter, right? We learned that in chapter 4.2. Having a method that takes ownership of an instance by just using self without the ampersand as the first parameter is rare. This technique is usually used when the method transforms self into something else and you want to prevent the caller from using the original instance after the transformation. So they said it's pretty rare usage, but there is a use case for it. So it's nice that they call that out. The main benefit of using methods instead of functions, in addition to using method syntax and not having to repeat the type of self in every method signature, is organization. We put all the things we can do with an instance of a type in one implementation block, rather than making future users of our code search for the capabilities of rectangle in various places in the library we provide. For example, before, if we wanted to see how we can use rectangle, we'd have to look for the area function and see, oh, it could take a rectangle. Here we can actually put it on that instance. So pretty cool, and similar to something we'd see. It's almost like, the struct itself feels like a type, right? It's got the typings there. The implementation feels like a class method, right? So it's almost like it feels like a class or a data class in Python. If you're familiar with data classes, it kind of feels like that. So kind of like an interesting mix of a type definition and an actual, class or some kind of, and that's why it's a struct. It's a structure. So pretty cool. Why the arrow operator? All right, let's see what they're talking about here. In C and C++, two different operators are used for calling methods. You use dot if you're calling a method. Where are we using the arrow besides the return type? Okay, let's see. If you're calling a method on an object directly, and arrow if you're calling a method on a pointer to an object and need to dereference the pointer first. In other words, if object is a pointer, object arrow something is similar to destructuring the object and calling something on it. Rust doesn't have an equivalent to the forward. Oh, so where's the operator? Doesn't have an equivalent to the forward arrow operator. Instead, Rust has a feature called automatic referencing and dereferencing. Calling methods is one of the few places in Rust that has this behavior, so it automatically handles this for us. So pretty cool. Here's how it works. When you call method with object.something, Rust automatically adds ampersand, mute, or star, so object matches the signature of the method. In other words, the following are the same. So here we're calling p1.distance and passing it p2. It's the same as doing this, so it's adding that for you. Pretty cool. The first one looks much cleaner. The automatic referencing behavior works because methods have a clear receiver, the type of self. So what they're saying there is, the reason this works is we know what the function method is receiving as input because it's always self. And we know what the type of that self is, that struct is. So that makes sense. So they can automatically do that in this case. Rust can figure out definitively whether the method is reading mutable self, mutating it using reading self reference, mutating it using a mutable reference, or consuming self without a dereference. The fact that Rust makes borrowing implicit for method receivers is a big part of making ownership ergonomic in practice. So it makes it a little bit nice for us, less to think about, but good to know what's going on under the hood there. Methods with more parameters. Ooh. Let's practice using methods by implementing a second method on the rectangle struct. This time we want an instance of rectangle to take another instance of rectangle and return true if the second rectangle can completely fit within the first or within self. I like this. Otherwise, it should return false. That is, we want to be able to write the program shown in listing 514 once we define the canHold method. All right, so here's the program they're writing here. So we can start coding that up here. So what we'll do is we will have, we can leave this stuff here. We can just make new ones. So I'm just going to copy this here. Paste it a bunch of times. And I'm going to call it rect. Let's call this one just rect. All right. And let's go ahead and call this rect1, call this one rect2, and call this rect3. And we have 30, 50. We're going to use 10, 40. And we're going to do 60, 45. Pretty cool. And here we're going to use print. I'm just going to copy these because I don't feel like typing that whole thing. Cool. All right, so can rect1 hold rect2? And what it's doing is calling rect1 can hold, passing it a reference to rect2. And here it's calling rect1 can hold and passing it a reference to rect3 because it doesn't want it to take ownership. Okay, and the expected output would look like the following because both dimensions of rect2 are smaller than the dimensions of rect1, but rect3 is wider than rect1. So rect2 can fit in to rect1, but rect3 could not because its width is far wider than rectangle 1, and its width is also far wider than the height of rectangle 1, so it couldn't fit either way, right? We know we want to define a method, so it will be within the implementation block of rectangle. The method name will be canHold, and it will take an immutable borrow of another rectangle as a parameter. We can tell what the type of the parameter will be by looking at the code that calls the method. Rect1 canHold passes a reference to rect2, which is an immutable borrow to rect2, an instance of rectangle. This makes sense because we only need to read rect2 rather than write, so we don't need to modify it. And we want main to retain ownership of rect2, so we can use it again after calling canHold method. The return value of canHold will be a Boolean. So let's try to write this out. So up here, implementation, we're going to write another function, canHold. It's going to take a rectangle. So in this case, it's not, it's going to have self, but it's also going to take another rectangle. So we're going to say other rect. And that'll be of type, it'll be a reference to a rectangle struct, and it's going to return true or false. And you can see the code is down below here. That's what we're going to be looking at. And what it's going to do, it's going to say if, so it's self.width is greater than other.width and self.height is greater than, and again we have to use other rect in our case, so how we declared it, rect.height. Just go back and do this, other rect. We're going to leave off semicolon, leave off the return, implicit return, pretty cool. Now we have our canHold method, and now if we run it, method not found in rectangle, rect1 canHold. Let's see. canHold takes self, other rect, returns a bool. Oh, I have to say it returns a bool. I left off the type. So it's saying, there we go, cargo run. There we go. Can rect1 hold rect2? Yep. Can it hold rect3? No. Pretty cool. When we run this code within the main function, we get our desired output. So this is how we can have multiple functions in the implementation block, multiple methods. Another useful feature of the implementation blocks is that we're allowed to define functions within implementation blocks that don't take self as a parameter. These are called associated functions because they're associated with the struct. They're still functions, not methods, because they don't have an instance of the struct to work with. You've already used the string from associated function. So we've been using them. Pretty cool. Associated functions are often used for constructors that will return a new instance of the struct. So string from, we gave it a string and it returned a new string struct. It didn't do anything with an instance. We didn't act upon an instance. So this is like if you've done JavaScript, right? You have your functions. For example, you have your static functions, your methods. You have instance methods, right, that operate on an instance of a thing. And then you have stuff like the constructor, which doesn't act on an instance, right? You use the class. So think of, if you're familiar with JavaScript, you have the instance function map. So you would say, you have an array, myArray.map. But you could also use array functions like array.map, capital A, or you could do array.isArray, right? IsArray you can't call on an array. You have to call array.isArray. So that's similar thing here. And we've done it with string from, right? So we used it to create a new string. Associated functions are often used for constructors that will return instance, right? Thus making it easier to create a square rectangle rather than having to specify the same value twice. So we can provide an associated function that would have one dimension to create a square. All right, let's do that. So we're going to go here. We're going to create function square, and it's going to take a size of type unsigned 32-bit integer, and it's going to return a rectangle. And all we're going to do is we're going to create a rectangle. We're going to leave off that semicolon, plus a return again, and we're going to say height. We'll do width first, like that. Width size, height size. Pretty cool. To call this associated function, we use the : syntax. So let's do that down here. I'm going to call it hip to be square equals rectangle square, and we'll do 42, and then we'll print to be square and we will run cargo run. Hit to be square rectangle cannot be formatted with the default formatter. Right, because it's struct. So don't forget, we got to do this. We'll pretty print it. And there we go. We have our 42 by 42 square. Pretty cool. That's awesome. Multiple implementation blocks. Each struct is allowed to have multiple implementation blocks. That's pretty neat. For example, listing 5.3 is equivalent to code shown in listing 5.6, which has each method its own implementation block. Why would we want to do this? There's no reason to separate these methods into multiple implementation blocks here, but this is valid syntax. We'll see a case in which multiple implementation blocks is useful in chapter 10, where we discuss generic types and traits. Okay, so not really a good use case here. Wouldn't add anything. It would just add complexity. So maybe not the best use case for this. Summary. Oh, we're done with structs already. Nice. Pretty powerful stuff. And we'll refactor. Maybe we'll go back and refactor our temperature to deal with this. Structs let you create custom types that are meaningful for your domain. By using structs, you can keep associated pieces of data connected to each other and name each piece to make your code clear. Methods let you specify the behavior that instances of your structs have, and associated functions let you namespace functionality that is particular to your struct without having an instance available. But structs aren't the only way you can create custom types. Let's turn to Rust's Enum feature to add another tool to your toolbox. Wow, pretty cool. Let's see, we're at 10:16, so we can still go into Enums. Let's see, how long is this one going to be? Not too bad, not too bad. We could start it. What I want to do before I start it, though, before I jump into Enums, and before we jump into Enums, let's go back, and what I want to do is refactor our Celsius converter to use these new structs, because I think this would be pretty powerful, right? So I'm going to go pull up temperature converter. So we wrote this code last time. Oh, didn't want that. And so what we had here is, just to walk through the code, we were reading from the user's input. Let me move myself over here so I'm out of the way. And we had our temperature, what we read from our user input, and we were letting the user type something like 32F, 0C, 500 Celsius, and we were doing the conversion, and we were detecting the unit and the temperature. And the way we were doing that was we were calling get temperature from string, which, if you see here, get temperature from string, temp string, and what it was doing was it was getting us a signed 64-bit integer and the string. in this case, the string slice. And the way we did it was we we read bytes from our string. We then searched for the location or the index of the F or the C character, so finding the presence of those characters. And then we took the temperature off the front, and then we took the character, and we were calling the temperature, and the character unit, and we were just returning them as a tuple. But let's create a struct for this. This is a good use case for a struct. So what we can do is out here, we can say struct, and we can call it temperature. And our struct temperature is going to have a temp, and that's going to be, again, a signed 64-bit integer, I think is what we're using, right? Yeah. And we went with 64-bit because we're doing division and conversions on it. So we're doing division math, so we need to deal with a floating point number. And then the unit, and in this case, the unit can only be Celsius or Fahrenheit. So we probably, when we get into that enum chapter, we're going to see that that's what this is used for. We're going to have an enum for either one. But for now, we'll just say that it's a string slice. But yeah, it would be great to just say that it can only be of type Celsius, that string little, or type Fahrenheit. But so let's do this. Let's just say for now it's string slice. And then so down here, what we would do is we would change this to say that it's going to return type temperature. And then we had to construct a temperature down here. So what we can do here is we can actually, we can just return from here. Or we can just do this down here. We'll say temperature, and we'll say temp. In fact, we'll rename temp across the board here. How do I get my multi-cursor working on Windows? I guess I can't. I have to change my bindings. Let's just go ahead and do this, and I'll show you why in a second. Because now we can just use temp down here. Pretty neat. And then for unit, we're gonna pass, we already called it unit, so we're gonna just stick with unit. And we can have an extra comma there, that's okay. So now we've refactored it. Let's see if this actually works. Oh, wrong project. Temperature converter, clear that, cargo run. Expected lifetime parameter, unit string. So this was similar to last time because we used the string there. And because we're trying to do stuff with it, I believe. So here we need, well, first we need to also change what we're pulling out. So get temperature from string returns a temperature now. So we need to adjust that. So let's say let temperature equal that, and then we're going to say our conversion here. So we're remember we're getting a full temperature type, so we could even specify. We could say this is of type temperature. We know that this function down here returns type temperature. And then what we'll want to do is pull out temp and the unit type, or temp and the unit Celsius or Fahrenheit from this. So, or we can just use them directly. So here we're going to say C is equivalent to blank F. And so we're going to say temperature.temp, and we're going to pass the temperature.temp. And here as well, .temp, temp, and here unit is going to be temperature.unit. We could also, degree might be the better way to say it than temp, you know, degree and unit. Let's just go with this though. So let's try to run this now and see if we might still get the same message because we didn't actually address that, but let's try it. Cargo run. Okay, expected lifetime parameter. And again, this was similar to what we saw here in our user, where we change these to strings. So again, if I run this one, go back here, structs, clear that, cargo run. Oh, cargo run, getting the same thing about the lifetime parameter. So what we'll do is we'll try adding the lifetime parameter. They didn't show us how to use it yet, so we're gonna have to try to figure it out. Consider introducing a named lifetime parameter. So let's try it. Let's go back to our temperature one, see what they suggest here. Cargo run. Okay, so it's saying, let's try this. And we'll have to figure out what this does, remember, in the later chapter, which will be fun. This is super interesting. I don't know what this is doing. But it seems to have worked. We'll have to check out chapter 10 for sure. So I'm going to put in 212F. And there you go, 212F is equal to 100C. So we've now written it to use structures, and it's a little more clear what we're dealing with here. And we could replace temp and use degree, but it's nice to have this structure. So pretty cool little refactor to use structures. Yeah, I think that's pretty awesome. So that is it for chapter 5. I think what we'll probably do is save Enums chapter 6 for, let's see, we're at 10:24. Let's see, we could probably, let's try to get through some of it. It doesn't look too bad. And we can always pick up wherever we leave off next time. It's a bit of a long one. Let's try to see how far we get with it. We got a good amount of time. Let's see how far we can get with it. I think it'll be worth it. And maybe we can restructure some of our code. All right, let's go into it. Enums are cool. Pattern matching is what I'm here for. I don't know if any of you know this about me, but I love the Elm programming language. If any of you are ever interested in learning that or messing around with that, I'd be happy to do a session on that. And pattern matching is one of the reasons why I love that language. It's also one of the reasons why I love Elixir, another really fantastic programming language, functional programming language. Okay, so enums and pattern matching, let's jump in. In this chapter, we'll look at enumerations, also referred to as enums. Enums allow you to define a type by enumerating its possible variants. First, and remember I said I wanted an enum for Celsius and Fahrenheit because 2 variants. First, we'll define and use an enum to show how an enum can encode meaning along with data. Next, we'll explore a particularly useful enum called the option type, which expresses that a value can be either something or nothing. So similar to like maybe types, if you're familiar with those in other languages. Then we'll look at how pattern matching in the match expression makes it easy to run different code for different values of an enum. We've used that before. Remember our result? We gave us back okay or error. We actually are using it right in this function here. We are pattern matching on an enum. Finally, we'll cover how the if-let construct is another convenient and concise idiom available to you to handle enums in your code. Let's go in. Let's do it. Enums are a feature in many languages, but their capabilities differ in each language. Rust enums are most similar to algebraic data types in functional languages such as F#, OCaml, and Haskell. Also Elixir. Pretty cool. All right, defining an enum. Let's look at a situation where you might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work with IP addresses. Currently, 2 major standards are used for IP addresses, version 4 and version 6. They're the only possibilities for an IP address that our program will come across. We can enumerate all possible variants, which is where enumerations get their name. You can enumerate them, right? Any IP address can be either a version 4 or version 6 address, but not both at the same time. So it can be one or the other. That property of IP address makes the enum data structure appropriate for this situation because enum values can be one of its variants. Both version 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type, however they can differ, right? We can express this concept in code by defining IP address kind enumeration, listing the possible kinds. So let's do that. So I'm going to go ahead and, as I've been doing before, let me just go ahead and put myself over here. I'm going to go back here. I'm going to create a new cargo new enums. All right, we got enums, so I'm going to go ahead and jump in there. Oh. All right. Let me close up some of these. All right, where's enums? Enums, main. All right, there we go. Move this down here. Move myself over here, and let's dive into enums. All right, so let's create this enum here. I'm going to create it out here. enum IP adder kind. And it can be v4 or v6, like an engine. All right, is now a custom data type that we can use elsewhere in our code. Enum values. We can create instances of each of the two variants of IP address kind like this. So let's try that. Oh, so look at this syntax here. We're using the : syntax. And let's 6. All right. Note that the variants of the enums are namespace under its identifier, and we use a : to separate the two. The reason this is useful is that now both values, IP address v4 and v6, are of the same type, IP address kind. We can then, for instance, define a function that takes a type IP address kind. So let's do that. So here we're going to have a function, routes. It's going to take IP kind of type IP address kind, and it's going to do nothing. And we can call this function with either variant. Using enums has even more advantages. Thinking more about our IP address type, at the moment, we don't have a way to store the actual IP address data. We only know what kind it is. Given that you just learned about structs in chapter 5, you might tackle this problem as shown in 6.1. So we have our IP address enum. We can create a struct called IPADDR to represent the address itself. We can say kind is of type IP address kind, and address itself is a string. Then we can create one. We can say let home equal IP adder. Kind would be address kind, v4, capital V, and the address, we're going to say string. So we're creating a string struct here from 127.0.0.1. And now we have an IP address. And then a v6 one down here, we're just going to copy this. This is called loopback. And the address is going to be : 1. And it's going to be of type v6. Pretty cool. All right. Here we define a struct IP address that has two fields: a kind, which is represented by the enum previously, and address is a string. We have two instances of this. The first one, it has a value of v4 for its kind. The second one has a value of v6 for its kind. We've used the struct to bundle the kind and the address together. Makes sense. We can represent the same concept in a more concise way using just an enum rather than an enum inside a struct by putting data directly into each enum variant. The new definition of the IP address enum says that both v4 and v6 variants will have associated string values. All right, let's try it. So this is like a much nicer way, right? Because you could say it's kind v4, and then you could put kind v6 here, right? There's nothing stopping you from doing this. But here we're going to say, and in this case, maybe there's not either, but we say that it has an associated string value. That's pretty cool. So let's do that. String, and we can get rid of this struct. And then, ooh, the way we instantiate it's a bit different too. That's pretty cool. So we do. Oops, sorry. I was going to try to maybe keep the old way so we can have a reference to it. Let me do that. Yeah, I do want to keep this. I'll just comment it out. So let's do this. Whoa, going too fast for you here. So what we're going to do is I just want to keep that old way, just so we have it. Yeah. And I'll put it here. All right, sweets. All right, there we go. And I'm going to just comment this out, comment these out, and I'm going to change this to have the actual string right there in place. String. And what we'll do here for the home and these, I'm going to comment these out as well, and we'll create new ones just so we have the old ones to look back on. And here is what we're going to be doing. We're going to actually create it like this. So pretty cool. So home equals IP adder v4, and we're doing passing it string from, and we're just going to take this here. Oh, 127.0.0.1. All right, and loop back is going to be loop back. It's going to be : : 1, and it's going to be of type v6. So different syntax here. We attach data to each variant of the enum directly, so there is no need for an extra struct. Pretty cool. There's another advantage of using an enum rather than a struct. Each variant can have different types of and amounts of associated data. Version 4 type IP address will always have 4 numeric components that will have values between 0 and 255. If we wanted to store v4 addresses as 4 unsigned 8-bit integers values, but we still express v6 addresses as 1 string value, we could do that. So that's pretty cool. Let's try that. So we're going to say this is of type 8, because remember it has to be between 255. That's pretty cool. And then here, instead of doing it like this, we can say 127, 0, and it's not a string anymore, so we can get rid of this. Pretty cool. And notice here we're saying, oh, also this is not kind anymore, this is just IP address. That's pretty cool. We've shown several different ways to define data structures to store version 4 and version 6 IP addresses. However, as it turns out, wanting to store IP addresses and encode which kind they are is so common that the standard library has a definition we can use. Let's look at how the standard library defines IP address. It has the exact enum and variants that we've defined and used, but it embeds the address data inside the variants in the form of 2 different structs, which are defined differently from each variant. So instead of using string U8, U8, it actually has structs for each of them. So pretty cool. So it's cool to see how the actual code, the actual thing itself is implemented. It's pretty awesome. All right. Let's see. The code illustrates that you can put any kind of data inside an enum variant, string, numeric types, or structs, for example. You can even include another enum. Also, standard library types are often not much more complicated than what you might come up with, just like what we saw here. Pretty cool. Note that even though the standard library contains a definition for IP address, we can still create and use our own definition without conflict because we haven't brought the standard library's definition in. So that's why it didn't complain. Talk more about bringing types into scope in chapter 7. Awesome. Let's go. Let's look at another example of an enum in listing 6.2. This one has a wide variety of types embedded in its variants. So here's a message. So it's got quit, move, that's probably like a point, write, change color. Message enum whose variants store different amounts of data. Quit has no data associated with it at all. Move includes an anonymous struct inside it. Write includes a single string. Change color includes 3 signed 32-bit integers. Defining an enum with variants such as the ones in listing 6.2 is similar to defining different kinds of struct definitions, except the enum doesn't use the struct keyword, and all the variants are grouped together under the message type. The following structs could hold the same data that preceding enum variants hold. So, quit message, move message, write message. This is like what they did with IP address. So pretty cool. But if we use different structs, which each have their own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined in listing 6.2. So they have a nice way to do it here. There is one more similarity between enums and structs. Just as we're able to define methods on structs using implementation block, we are also able to define methods on enums. Here's a method name call that we could define on our message enum. So the message enum is string. They define a message call. And here we're saying let m equal message write which is write string from hello, and then they're saying m.call. Method body would be defined here. Interesting. So quit message, move message, write message. So here they have a single method with call and the message there. It's pretty cool. The body of the method would use self to get the value that we called the method on. In this example, we created a variable m that has the value message, write, string from hello. And that is what self will be in the body of the call function when m.call runs. Let's look at another enum in the standard library that is very common and useful, option. This is the big one. This is a really good one. Excuse me. The option enum and its advantages over null values. In the previous section, we looked at how the IP address enum lets us use Rust's type system to encode more information than just the data into our program. This section explores a case study of option, which is another enum defined by the standard library. The option type is used in many places because it encodes the very common scenario in which a value could be something or it could be nothing. So, almost like the maybe type, right? Sorry. Expressing the concept in terms of the type system means the compiler can check whether you've handled all the cases you should be handling. This functionality prevents bugs that are extremely common in other programming languages. So this is exactly the type of thing we're looking for here, like the ability to make sure that we're handling both good and bad scenarios. So we saw it already again in our temperature converter where we handled the OK and the error. So that's like one option of matching, but the option is something like in JavaScript, we go and get asynchronous data, right? A promise. A promise could resolve or could reject. You have to handle both scenarios. So an option is pretty interesting. I'm sure they'll have similar use cases. Programming language design is often thought of in terms of which features you include, but the features you exclude are important too. Rust doesn't have the null feature that many other languages have. Null is a value that means there is no value there. We've seen this, right? You have none in Python, right? You have null in JavaScript, nil in Elixir. Null is a value that means there is no value there. In languages with null, variables can always be in one of two states, right? They can be null or not null. In 2009 presentation, Null References, the $1 billion mistake, Tony Hoare, the inventor of null, has this to say. I've seen this quote before. Let's check this out. I call it my $1 billion... Should I do a voice? I don't know what he sounds like. Let's try one. I call it my $1 billion mistake. At the time, I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all the use of references should be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This has led to innumerable errors and vulnerabilities and system crashes, which have probably caused $1 billion of pain and damage over the last 40 years. Wow, powerful stuff, Tony. Powerful stuff. And it's probably true. It's probably true. I mean, I wouldn't blame anybody, right? But it is probably true because it does create. You get null pointer exceptions, right? How many times have you seen those? How many times have you seen cannot access blank of undefined, null, passing null around? Problem with null value is that if you try to use a null value as a not null value, you'll get an error, right? You try to call a function on an undefined or a null, you'll get an error. Because the null or not null property is pervasive, it's extremely easy to make this kind of error. However, the concept that null is trying to express is still a useful one. A null is a value that is currently invalid or absent for some reason. It has no meaning yet. The problem isn't really with the concept, but with the particular implementation. As such, Rust does not have nulls. No one knows. But it does have an enum that can encode the concept of a value being present or absent. This enum is option, and it's defined by the standard library as follows. Option T, this is generic. You've seen this before. Some T, none. So it's option of type. So generic means you can provide it the type that it will be. So for example, we can do an option of type string, capital S, and then it would say it's some string or nothing. The option T enum is so useful that it's even included in the prelude. You don't need to bring it in to scope, right? In addition, so are its variants. You can use some and none directly without the option prefix. The option T enum is still just a regular enum, and some T and none are still variants of type option. The T syntax is a feature of Rust we haven't talked about yet. It's a generic type parameter. You've probably seen this in other languages. If you use TypeScript, if you use Java, you've seen this. If not, don't worry. We'll get into it. It's not that complicated, and it just looks intimidating, but it's not too bad. It's a generic type parameter, and we'll cover generics in more detail in Chapter 10. Chapter 10, what? Is it going to be loaded? Chapter 10. It seems like they're pushing everything up. Chapter 10. Hold on. Really? Seems like it's going to be loaded. We'll see. We're going to need 2 sessions for Chapter 10 based on all the stuff they've been pushing off to Chapter 10. For now, all you need to know is that T means the sum variant of the option enum can hold a piece of data of any type. It's a generic type. Here are some examples using option values to hold number types and string types. So some number, some 5, some string, absent number, option I32, none. So it's letting us set it to none. If we use none rather than some, we'll need to tell rest what type of option T we have, because the compiler can't infer the type that the sum variant will hold when it actually has a value, right? If it has just none, it doesn't know what it's supposed to be. When we have some value, we know that the value is present and the value is held within the sum. When we have a none value, in some sense, it means that the same thing as null, we don't have a valid value. So why is having option T any better than having null? Well, we know the type it should be, right? In short, because option T and T, where T can be part of any type, are different types. The compiler won't let us use an option T value as if it were a valid value, as if it were definitely a valid value. For example, this code won't compile because it's trying to add an signed 8-bit integer to an option signed 8-bit integer, which may or may not be present yet, right? So here you see it. If we run this code, we get this error. No implementation for aborting due to previous error. Intense. It's pretty intense. In effect, this error message means that Rust doesn't understand how to add a signed 8-bit integer to an option signed 8-bit integer because they're different types. When we have a value of type signed 8-bit integer in Rust, the compiler will ensure that we always have a valid value, right? We're never going to have none. We can proceed confidently without having to check for null before using the value. Only when we have an option or whatever type of value we're working with do we have to worry about the possibility of not having the value. It's not there. It's optionally there, right? And the compiler will make sure to handle this case before using the value. In other words, you have to convert an option to a T before we can perform the T. So in this case, we'd have to convert the option of the signed 8-bit integer to an actual 8-bit integer before we can perform this operation. Makes sense. Generally, this helps catch one of the most common issues with null, assuming that something is null isn't null when it actually is, right? Misusing it. Not having to worry about incorrectly assuming a not null value helps you to be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type of the value option T. So if you need to have something that's optional, something that maybe it's a future, right? It may not have value yet until you make some call. Maybe it's none until you've defined it or run through a function. We could have done this with temp, right? We defined temp here by default as Fahrenheit. We could have defined it as none and said that our unit was an option string, and then we'd have to convert it to a string before we used it, right? We didn't need to do that, but it's better, I think, probably more useful when you're dealing with futures or asynchronous stuff like standard in and standard out, right? It's empty until someone types, so pretty cool. Not having to worry about incorrectly assuming not null value helps you be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making it a type option T. Then when you use that value, you're required to explicitly handle the case where the value is null. Everywhere that a value has a type that isn't an option T, you can safely assume that the value isn't null. This was a deliberate design decision for Rust to limit null's pervasiveness and increase the safety of Rust code. I love that. Love that. So how do you get the T out of the sum variant when you have a value of type option T? So you can use that value. The option T enum has a large number of methods that are useful in a variety of situations. You can check them out in its documentation. Become familiar with the methods on option T will be extremely useful in your journey in Rust. So I'm going to pull that up in a separate tab. In general, in order to use an option T value, you want to have code that will handle each variant, the match statement, the pattern matching. You want some code that will run only when you have some T value, and this code is allowed to use the inner T, and you'll want some code to run when you have the none value, and that code doesn't have a T. The match expression is a control flow construct we've seen before that does just this when used with enums. And we'll run different code depending on which scenario we have, a none or a sum. All right, so we're not going to go into the next part yet because we're getting close to 11, and the next part is quite long. So we're going to save that. That's going to be the interesting part on pattern matching for next session. Let's take a quick look at the option documentation. I know, not very, we're reading docs on stream. Come on. Let's see though. So we have the option implementation. So these are, again, implementation for option T, is sum. So these are like the functions that it implements, the methods, I should say. Is sum. Bool is none. So you can check if it's sum. You can check if it's none. You can check if it contains. Pretty cool. So here they're saying sum2 contains 2. As ref, as mute, as pin ref, as pin mute, expect, unwrap or. These docs are pretty nice. I like the formatting too. So very cool what we can do with this. So good to have a reference to these. That's awesome. All right. Well, that's where we're going to call it for the night. Thank you for stopping by. If you're watching this on YouTube after the fact and not on the live stream, thank you for viewing. And if you like what you see, definitely hit that subscribe button and you'll get notified when more videos come out. You can follow along. If you're on Twitch and you're catching us on Twitch, any follows appreciated, so you can check us out and see when we're back on here learning. Again, my schedule is Tuesday nights, 9 p.m. to 11 p.m. We haven't yet added another day. We may do it. We'll probably stick to this for a little while, but we're going to keep going with this until we get bored. And maybe in between, we may do some one-off sessions. I won't interrupt the Tuesdays. I would add another day should I decide to do that. Like I mentioned, we check out Elm, maybe do something with Gatsby for building a portfolio site. Who knows? The options are limitless. Maybe we just start using what we know of Rust to build some small programs. That could be fun. But I think learning pattern matching is going to be key. And just kind of browsing at some of the chapters that we have coming up. Enums, pattern matching, managing growing projects and packages, crates and modules. I think we can start to really write some programs once we complete chapter 6. Chapter 7 is more about project structure. Common collections is going to be important, storing lists of values of vectors for us to be able to write programs and things like that. Error handling, generic types. So we do get more into stuff that's, language features that help us write programs. But I think after we finish chapter 6, which we're on, we can try writing some basic programs. And then what we'll do is when we learn more, kind of like what we did when we learned Struct, we'll go back and we'll refactor. And we'll lean on that compiler to help us do that refactor, right? So I'm excited for that. So thanks for stopping by live. If you're here on Twitch, thank you for stopping by. I appreciate it. Clam Watson, happy to have you in the chat. If you're watching live on YouTube, thank you for coming. Thank you for viewing. I hope you enjoy what you see. Check out some of the other videos. Again, YouTube, just search my name. I'll also paste the link in the chat here so you can find all that stuff. Let me just view it not as subscriber. Why does it say view as subscriber? That's weird. Woo! So pasting this here. For anybody who catches on Twitch, you can catch all the previous videos there. Again, follow me on Twitter if you want updates on when I go live. I update the day of, usually on Tuesday. I also post midweek. You'll see me post stuff about when the video gets uploaded onto YouTube. Video is always uploaded the following morning. First uploaded in the middle of the night in standard def and then in high def the following morning. So wait for that. And again, you can find all the code here. I'll be pushing up to this repo. Learn Rust together. Learn Rust live at Tom McGurl. I'll post the link in Slack to this, and you can also find it in the description on those YouTube videos. So appreciate you stopping by. Appreciate you watching if you're viewing over on YouTube. Thank you again. My name is Tom McGurl. Information above. Rustations. We're becoming Rustations together, and it's been a lot of fun. Really appreciating it. So everybody have a great night and keep on coding.